So now there were some interesting questions that I had gotten when we were discussing the data path architecture, right? One of them was just pointing to the fact that in every cycle you have to be aware about whether the control signals are going high at the right time. There could be a one cycle delay from input changing to the control signal going high, so you have to keep track of it. Another important question that I got was this. Okay, let's say you have a clock edge occurring and that is triggering some change in the Y. Based on this change in the Y, you have lot of processing happening, and all of this processing should be completed before the next clock edge that is occurring. Is that clear? So you have one clock edge that is occurring. So let me sketch a clock edge. Right, so I have shown two rising edges for the clock. Let's assume that the active edge, that is all the flops, are sensitive to the positive edge of the clock. Now at this edge, your output is going to change, right? Then based on that output of Y, you have lot of combinational circuit that need to operate, and finally your D input to the flop has to be set correctly before the next rising edge in the clock. Right? So as you can imagine, this is going to put some constraints on how far apart these two rising edges should be. Right? So we are going to look at this particular analysis right now, which depends on everything related to the delay within the circuit. Right? Now you could construct your data path correctly, but if you happen to clock it with a very high frequency clock, all of this information will not get executed within this one clock period. So you could have a perfectly working Verilog code, which is synthesizable, it gets translated into hardware, but just because you gave a wrong clock period, your circuit might not function. Right? So to understand this, we first have to go through some definitions. We first have to understand how we are going to define the delay. Right? I will take a very simplistic definition for delay for now. Let's say you have an inverter. If you give a rising edge at the input, you expect to see a falling edge at the output. Right? But of course, these edges are not going to be sharp. It doesn't have an infinite slope. In practice, you will have edges that look like this. So let's say this was the input, and you get an output that looks like this. Now to define the delay between these two signals, for now I will look at the 50% rise point, meaning if your input was rising from 0 to VDD, then at VDD by 2, your input is halfway there to the final value. Similarly, let's say your output was falling from VDD to 0, then again at VDD by 2, your output is halfway to the final value. Right? So we are looking at the 50% points, and then we'll simply look at the delay between them. Right? And this is what we are going to call as a delay for all of our circuits. Now there are more nuanced definitions that you can look at for delay definition, but for now, let's say we are happy with this definition. Now similarly, let's say you have an AND gate. You can identify a delay from its input to the output. Okay. Now let us look at a flip-flop. How will you define its delay? So you have a clock port, you have a D port, and a output port Q. Right? From where to where should you define your delay, and how would you go about defining this? Setup and hold are not delays. Right? They are constraints associated with the flop. Right? So I'll come to the constraints. But if I have to define a delay, right, my input is changing, my output will also change, right, at some point. Now I have to define a delay from some input port to the output port. Right? Which delay do you think is the most appropriate definition? Okay, so let me set up the case for you. Let's say I have a clock signal. Right? And let's say my D is changing. So prior to this, let's say the value was D0. This is D1. and then it became D2. When will my Q change? Will my Q change corresponding to this? No, Q is going to change corresponding to your clock edge. Once the clock edge occurs, your Q is going to change corresponding to that. And at this clock edge, it is going to latch the value. What value will it latch? D1. Right? So now this change has happened because of this clock edge. Right? Now can you tell me what delay I should be looking at? Should I still be looking at a D to Q delay? Right? I should be looking at a clock to Q delay. Right? So that is what we will define. So this becomes our clock to Q delay, or for now I'll simply call it as TCQ. So we have defined TCQ, which is clock to Q delay. Okay. Now this is a physical delay that happens when your clock changes. Your Q is going to change sometime after the clock has received an active edge. Right? All that I mean by the active edge is the fact that you are responding only to one type of edge. This edge makes no difference for your clock. Right? So I'm calling this edge as the active edge. That's all. Okay. Now let us look at the setup time and the hold time behaviors. So setup time is not a delay. This is a constraint associated with your clock. Now all that it says is that if you have an active clock edge, and let's say your D is changing, say D0, D1, and you want to latch D1 to the output, right? So then D1 has to of course change before the clock edge, but in particular it has to be stable some time before this clock edge. Okay? So I'll represent this as TSU. So the setup time is the minimum time before the active clock edge that your data should be stable. That your data should be stable so that that particular data gets latched correctly. Is this okay? Okay. Now what is hold time? So there is a minimum time after the active edge of the clock where your data should remain stable so that the same data is then latched correctly at the output. So it's minimum time, the rest of it remains the same after the active clock edge, that the data should be stable so that it is latched correctly. The names are actually very indicative. Before the clock edge, you have to set up the data. After the clock edge, you have to keep holding the data. Right? Now together, this window is sometimes called as setup hold window. It's also sometimes called as the aperture. Right? So in effect, during this portion, your data should not toggle at all. Right? If that is satisfied, then whatever is the value of the data during the setup hold window, the same value will appear at the output of the flop. Okay. Now the origins of the setup and hold time, we can cover it only after we know the internals of the flip-flop. But for now, this is sufficient to carry on with our calculations. Now a quick question. Let's say I give you two flops, flop 1 and flop 2. Right? One of them has a lower setup hold window than the other. Let's say flop 1 has a lower setup hold window than flop 2. Which one will you use in your designs? Like lower one, right? Because you are now much more immune to variations happening in the data. Alright, so now let me take a basic example. So what we know now is anytime you have a combinational circuit, it will have some delay associated with it. For now, I'll represent it as T-comp. And anytime you have a sequential element like a flip-flop, you will have a clock to Q delay associated with it and two constraints, setup time and hold time associated with it. So the moment you design your flop, these values are fixed. And then you have to make sure that in your bigger design, all of these constraints are satisfied. So now let me set up a scenario that we have already seen. Let's say you have a flop. You are feeding in some DA to this. Then you have a combinational circuit followed by another flop. So the same clock signal is going as input to both. I'll call this as QA. This is DB. This is QB. Right? This is something that you have seen before also, where one flop output goes through a combinational logic and then feeds into the other flop's input. Right? Nothing new here. Now here, your flop A is launching some data and your flop B is capturing the data. Right? So you have a launch and a capture flop. So this is launching, this is capturing. So let me now sketch a clock signal. Let's say your data was initially D0, so I'm looking at DA. I'm going to assume that it was set up correctly before this active edge. Let's say then this is D1. This changes here to D2 and it remains like this. Tell me how your QA is going to look like. So initially it will have some value, right? After the first rising edge, so if this is your clock rising edge, after a clock to Q delay, your QA is going to change. What happens to DB? So we will assume that this has a TCQ clock to Q delay. For now, I'll assume the same TCQ for both. Right? Let's say this has a combinational delay given by T-comp. When does DB become steady?
After T-comp.
So this is value corresponding to D1. So I will directly show that D1 has been latched. So after this edge, you will have a delay of T-comp and then you will have DB, which is a function of D1. Right? Some combinational logic. So your D1 appeared at QA, then some operation happened on it, and then you have the corresponding output here. Let me mark all the delays so far. So this is TCQ and this is T-comp. Now, this edge has launched our data, right? In our analysis, we have launched our data from flop A at this edge, right? The same data, D1, needs to be captured at this edge. Right? The output corresponding to D1 needs to be captured at this edge. Right? So what do I need to look in flop B for that? The data has to be set up one setup time before the active edge of the clock. Right? So I have to make sure that your data is ready at least one setup time before the capture edge of the clock. Right? Is that condition satisfied? Right? This is nicely satisfied. Okay. So let me write out this condition. So what we need is TCQ, that is this. So I can pull out all the numbers closer to the clock. So you have a TCQ, then you have a TComp, and then you have this TSU on this side of the clock, right? So TCQ plus TComp plus TSU. Can you tell me a constraint based on the overall clock period? This is your whole clock period, right? This has to be lesser than the overall clock period, right? And we are lesser by, so we have so much buffer now, right? Which means I could have designed my clock period to be even smaller, okay? So in this particular case, I'm going to rewrite the equation. So I'll say that T clock minus TCQ plus T combinational plus TSU. This has to be greater than or equal to 0. Equal to 0 is the minimum constraint that you can have, right? Now let me say this is equal to, I'm simply going to call this as slack, right? Because this is the buffer period you have here, right? You had so much extra time within the clock period, okay? Now quickly tell me, do you want the slack to be positive or negative? You want your slack to be positive. So in particular, because this slack has been calculated by checking for the setup time, this is called as the setup slack. Right? So you want this value to be positive, and what does it mean if this is 0? Then you have just about met your timing constraint, right? If your clock period goes any smaller, your circuit will not function, right? So this also tells you what is the minimum clock period with which you can operate your circuit. Okay, so tell me, what is the minimum clock period? So T clock min is simply equal to TCQ plus TComp plus TSU, right? And once you have the minimum clock period, you can calculate the maximum clock frequency that your circuit can operate at. That is simply be equal to 1 by T clock min. Right? So now when you look at all the processor specifications and it tells you that the fastest it can go is at, let's say, 3.5 gigahertz, that means there is some path in that circuit for which this was just about met. Is that clear? Any questions on this? Okay, so then we move on to, so we want our data, so at the capture edge, we will want it to be stable for a range of setup and hold window, right? So let me mark out the setup is already analyzed. Let me mark out the hold window here, okay? And let's analyze what happens during this hold period, okay? So now at the clock edge, your A is still, so at this clock edge, your A is still getting clocked, right? Which means your QA is going to change. Is that clear? So let me sketch QA there. So your QA is going to change after what time? After a TCQ. Right? Which means your DB, right? This has changed. So this will change after the combinational circuit state. Right? So this is your TComp. Right? Now we don't want this change to happen during the hold period. Correct? This change in your data should not happen when the flop is in its setup window or when it is in the hold window. Right? Now that this is happening corresponding to the clock edge, this change could have potentially happened during the hold window. Is it clear? Now, what is the condition that ensures that the data is stable during the hold window? You want your hold time to be lesser than TCQ plus the combinational delay. Is this okay? Now, can you tell me how I can write it in terms of the So we have the constraint TH should be lesser than TCQ plus the combinational delay. Now I want to write it in terms of a slack, right? Can you tell me what would be the hold slack?
At TSU,
So how did we define our setup slack? We looked for by how much, what buffer was there in meeting that constraint, right? So now the constraint we want to meet is this.
TCQ plus T component.
So you can potentially say that this should be equal to TCQ plus TComp plus, sorry, minus TH, right? Now when the whole slack is positive, does it mean we have met the condition or we have failed to meet the condition? We have met the condition, right? So whenever your slack is positive, it means that you have met the condition. And if you have not, if you have a negative slack, then you need to correct something in your circuit so that you can get back to a positive slack. Okay, is this okay? Then let me give you some numbers. So let's say the combinational delay is 6 nanoseconds. For both the flops, the setup time is 1 nanosecond, the hold time is 3 nanosecond, and the clock to Q delay is 2 nanosecond. And let's also assume that the T clock is equal to 8 nanosecond. Can you quickly calculate what is the setup time? Sorry, what is the setup slack? Check if the setup time constraint is met and tell me what the setup slack is.
Can we have TCQ less than?
So the TCQ can be lesser than TH also. It depends on how the flop is implemented.
But once the output has changed, I will not hold.
Once the output has?
Once the output has changed, why do the hold?
Okay, I understand your question. Sometimes what can happen is if your data changes during that window, even though the output has changed, it can again flip. Okay? So after this is your launch flop, this is your capture flop. Let's assume that A has launched, so this is A, this is B. This has launched at this edge, right? You know that the data should be set up before the setup time of flop B, right? And once the data has been launched, first you will have a delay of TCQ of A for the output to reach here, then another delay of combinational circuit for the output to reach here, and this whole thing should be equal to T clock. Right? So the condition is T clock has to be greater than TCQ of A plus T combinational plus the setup time of B. And for the slack, so now we are looking at the setup slack. This should be equal to so much. Okay. What is the result you get? So this is 8 minus TCQ is 2 plus 6 plus setup is 1. What do you get? Minus 1 nanosecond. Right? Now can you tell me what is the minimum clock at which, so clearly for a clock of 8 nanosecond, the circuit is not going to work. Right? So what is the minimum clock period at which the circuit can safely operate? It will be 9 nanosecond. Right? So if this value was equal to 9, then your slack would have been 0. Okay. Can you calculate the whole slack? So again, this is we are looking at whether the data is correctly captured at this edge, which means we have to retain the data to be stable for a T hold time. Now at the clock edge, this output is going to change after a TCQ A, and then your D is going to change after a delay of T comp. Right? So the hold condition is going to be your TCQA plus T comp has to be greater than TH. So you can define your hold slack as this minus this. Right? TCQA is, so this is 2 plus 6 minus 3. How much do you get? Yeah. So the hold condition is met, but your setup condition was not met. Now, let us analyze how we should do this whole exercise if there is a delay in the clock path. This is data Q. Let's say you have a combinational circuit here. D, Q. And let's say you had a buffer in this path, and this buffer had a delay of TD. So this has some TCQ and T setup and T hold associated with it. The combinational circuit has a T comp associated with it. I'm going to call our first flop as flop A. This is B, and as before, we'll use, this is DA, QA, DB, and QB. Right? Because the clock signals are different, I'll call this as clock A, and this is clock B. Let me sketch out the clock for you. This is clock A. How will clock B look like? How will clock B look like? It will be slightly delayed. Right? Now, which is your launching clock edge? Right? So, you're launching here, and where do you want to capture this? Yes. So, you want to get it captured at this edge. Okay. Now, can you give it a try and give me a expression for a constraint for meeting the setup time and something for meeting the hold time? Does it add in both cases? Okay. So then let's analyze, right? Let's say this is your DA. I need to look at QA and DB. I'm going to assume that DA was set up correctly in the beginning. So this is, let's say, D1, D2. When does QA become ready? After the clock edge, we have to wait for a clock to Q delay. Right? After this clock to Q delay associated with this, you have the value D1 appearing at QA. And this will remain steady till the next clock edge. What about DB? So from here, you need to wait for a combinational delay. Right? So this is T comp. Okay. So from this clock edge, you have TCQ followed by T comp, and your data is ready. Right? And this needs to be latched at this instant. Right? So between the clock being launched, between the data being launched and it being captured, this is the window you have. Right? And what is this window? That is going to be T clock plus TD. So now your condition is T clock plus TD has to be greater than TCQ plus T combinational plus the setup time. Is this clear? So which means your T clock now has to be greater than TCQ plus T combinational plus T setup time minus TD. So is this TD helping you or is it making it worse for you? For the setup time, this is helping you, right? Because larger the delay you put here, the smaller your clock period can be. Right? So larger your delay is, the smaller your clock period is going to be. Right? So if you kept increasing TD, it looks like you will be able to make your circuits work faster and faster. Right? But what is the bottleneck?
You will just shift it to the point that within the same on the same edge it will just update.
But there is something else that is becoming a bottleneck even before that. Right? Can you check for the hold condition here?
That maybe will.
Right? So again, our edge at which we are capturing is this. So I need to look for the setup time before this edge and a hold time after this edge. Right? So now when the next data gets launched at this edge, correspondingly your QA is going to change. So after a clock to Q delay of the A, your QA has changed, and after another combinational delay from this point, your DB will also change, right? Which means from this edge, after one clock to Q delay and another T combinational delay, now your output has changed, right? But your output should remain steady till this point. Right? So how can you write the constraint now? So your TCQ plus T combinational should be greater than, what is this delay? This was the clock delay in the clock path. Should be greater than TD plus TH. Is this clear? Right? So having a TD helped with your setup time, but it is going to make meeting this constraint harder. Okay, any questions on this? Okay, so now let me give you one more sample problem. So let's say you have some combinational circuit here, and this is taking some output in1 from outside, and we'll for now assume that the in1 has been set up correctly. This is D, Q. So the output of this is being fed in to this flop. I'll call this as flop A. This is flop B. Right? You are asked to analyze whether this circuit is meeting all the setup and hold constraints. So I know I have not given the value, but let's say you are asked to analyze whether the circuit is meeting the setup and hold constraints, and you are also asked to check what is the maximum clock frequency at which this circuit can safely operate. Or in other words, you have to find out the minimum clock period at which this circuit can operate. Right? Can you quickly tell me how you would go about analyzing the circuit? What is your launch flip-flop? What is your capture flip-flop? Question is clear? So launches? So you can launch at A and then capture at B. Right? Similarly, you could be launching at B and then capturing at B. Capturing at A. Right? So there are two paths that you now need to analyze. Right? So if you have to check for setup and hold conditions, you have to check this for both the paths. If you find out what is the minimum clock period at which the circuit can operate, you have to find out the clock period, minimum clock period at which both these paths can operate, and then you have to identify whichever is the largest among the two. Right? So let me give you some numbers. Can you solve this? So let's say this has a 4 nanosecond delay. This has setup equal to 4 nanosecond. Clock to Q equal to 3 nanosecond, and TH is 1 nanosecond. Here the setup is 4 nanosecond Let's say the clock to Q is 8 nanosecond. You can simply calculate and tell me the minimum the minimum clock period at which this can operate. So when you're looking for the minimum clock period, which constraint are you trying to solve? Setup or hold? Setup, right? Because in none of the hold equations, your clock period is present. So what do you get? So for launching at A and capturing at B, your condition is TCQA plus TCOM plus TSU of B. This has to be smaller than your T clock. Right? And what T clock do you get for this condition? This will be equal to 11 nanoseconds. Now for launching at B and then capturing at A, the condition is much simpler. You have TCQB plus TSU of A has to be smaller than the clock period. And this gives you T clock of, so I'll call this as 1, this is 2. This gives you T clock of 12 nanosecond, right? So you have two parts. One will work correctly if it's operated at 11. The other will work correctly which is if it is operated at 12. Now what is the minimum clock at which this circuit can operate correctly? That will be 12 nanosecond, right? So finally your T clock minimum will be maximum of T clock 1 and T clock 2. Okay? Alright. Now let's say you fabricated a chip, right? You designed for it, you fabricated it, and you got the die back, and when you are testing, you realize that the setup time has not been met. Right? What can you do now? Right? The solution is very simple. You can increase the clock period. Right? If your circuit is not operating at 5 gigahertz, check if it is able to operate at 4.5 gigahertz. Right? So you can increase your clock period or decrease your clock frequency, and your circuit is very likely to work if it is a setup time issue. Right? What if the hold constraint was not met? But the circuit is already in your hand, right? How will you increase the combinational delay now? So your die is fabricated, you have the IC on your hand. You can't do much, right? Unless you build in specific provisions during the design time to increase certain combinational delay or decrease it, you can't do much. Yes.
Over there, shouldn't it be kind of maximum of TCQ B and T hold B? Because it holds that even after TCQ, hold can be greater and it can flip.
I didn't follow the question.
In the second part.
So are you talking about this equation?
Yeah. Shouldn't it be maximum of TCQB and T hold B?
Maximum of TCQB and T hold B. So in checking for the clock period, hold is never checked.
But if the value, if the input changes and hold time is greater.
So you have to check for the hold constraint separately. For the circuit to operate, both the setup and the hold constraint should be verified. But determining T clock, because T clock is only a function of the setup time, that you don't have to check the T hold conditions at the time. Provided your flop is completely correctly characterized, if it has a setup time and a hold time, then you check for the setup time constraints that ties to the clock period. Check for the hold constraints that doesn't tie to the clock period. So that is it. Yeah. Now let's say it was during the design phase that you find that in a particular path the setup constraint is not met. Right? Then what can you do? During the design stage, right? So now you can go and manipulate your circuit. Setup is not met. What all can you do? You could introduce a delay here. You could reduce the clock period. You could try and reduce the combinational circuit delay, right? Or if there is another flop with a smaller setup time, use that. Right? Now during the design phase, let's say your hold constraint is not met. Then what can you do? Then you can increase the combinational delay here. Okay. So during design phase, hold is something that you have to pay special attention to, because if you are not able to fix it during the design phase, your chip is gone. Right? If it is setup, ideally you should fix setup issues also, but at least you have some leeway after that. Okay, so we can have the quiz now.